In this one short video, we are going to have a detailed discussion of relations. Now, relations might not be a very big chapter, but usually the questions are repetitive, and if you prepare it well, chances of you getting that question right are really high. So we are going to systematically start with the weightage of relations in JEE Mains. Then we are going to go into the syllabus comparison between 24 and 25. Then we are going to dive into the mind map and see what actually the topic entails. And then we are going to systematically analyze the problem types in relations. Now, before you start this video, there is a do, there is a don't. The do is don't watch this video like you're watching a movie. Be alert, see what kind of problem solving techniques I am using in solving various types of questions. Make a note of those problem solving techniques based on problem types. A don't is, this video is not meant for a beginner who has not done the basics of relations. If you are one of those persons, then go and watch some basic video or revise this topic from NCERT, understand the basic definitions, and then come and watch this video. You are going to really enjoy it. So without any further delay, let us start with it. Now, if you look into syllabus comparison, the syllabus only tells there are 3 points in the syllabus. The first one is nothing but the definition of relation, types of relation, and equivalence relation. Now, this has remained same from 23 to 25 and 24. If I go into the mind map of relation, you can see that the discussion starts with the definition, where we understand what is the domain, codomain, and range of a relation. Then we go into the P&C part and understand how many relations are possible in a context and what is inverse relation. Then we move towards type of relation and understand what are void and universal relation, what is an identity relation, and what is an equivalence relation. Equivalence relation is very important for JEE Mains. And hence we go into the details of equivalence relation and understand that a relation that is reflexive, symmetric, and transitive at the same time will become an equivalence relation. And then we discuss problems based on it. If I move towards this first problem, right, it talks about domain and range. So there was this question asked in 2020 that talks about a relationship between x and y. And in relationship, the question clearly says that what is the domain of inverse function. Now see, we know that for inverse function, if there is a relationship R, if the domain is D and range, we have this range corresponding to this, for inverse function, it will get interchanged. The range will become domain, domain will become range. So what we need to figure out is this function that is given, what is the range corresponding to this, and range means nothing but the value of y. So what we need to find is the valid values of y. Now if I want to find this, it is very simple. So the range of y square, so you can see that if I put x equal to 0, the maximum value of 3y square needs to be smaller than 8. And corresponding to this, y square should be smaller than equal to 8 by 3. Now since y, x and y both belongs to z, what are the possible values of y that we can put here? I can put y is equal to 0, minus 1 and plus 1. If I put 2, it will become 4 and that will exceed 8 by 3. So that is not possible. So these are the only 3 values that are possible. You can see that option C matches. Now this type 2 problem is based on equivalence relation. A relation which has these 3 ideas. First, it should be reflexive. Reflexive would mean if there is an element a comma a, it should always be there in the relation for all a and belongs to set A or which the relation is set up. So you can see that if this happens for all the elements, it will become reflexive. For symmetric, we have an if then else condition. If, so it is not valid for all the elements. If a comma b is there, then b comma a should also be there. Then it will become symmetric. And for the third part, that is transitive, this also needs to happen. Now for transitive, the condition is very simple. If there is a comma b and b comma c, both of these pair, then there should be also a comma c. This should also be there in relation R. So the relation, this idea of equivalence relation is very simple. If a relation is reflexive also, that would mean a comma a, all such elements are there. Symmetric, if a comma b is there, b comma is there. And transitive, if a comma b and b comma c both are there, then a comma c is also there. If all these 3 conditions satisfy, we will call that relation as equivalence relation. Now we are looking into first problem type where the relation is given in the form of elements or Rooster form. Let us see this question that came quite early. And when there was not JEE Mains, but another exam that used to replace JEE Mains, that JEE Mains replaced, and that was nothing but JEE. So this is quite an old question that was asked in 2005. This question says that if you have a relation that is given to you in the form of elements here, they are asking that this is defined over a relation A that is given to us. Then the relation is reflexive, transitive, reflexive only, equivalence, all of these conditions are given to us. Now see, for this to become reflexive, all the elements with pairs with themselves should be there. So 3, 3, 6, 6, 9, 9 and 12, 12 should be there. If this is there, it will become reflexive, and you can see that all of these elements are present. So this is reflexive. The reflexive part we have done. Now let us move towards symmetric. You can see that there is 6, 12 but not 12, 6. So symmetricity is not there. And third, for transitive, it is again an if then else condition. So you can see that 6, 12 ka pair is there, but the first element 12 is not present, so we can't use this. 3, 9, but first element 9 is not present, so we can't use this. 3, 12, but 12, something is not there, we can't use. 3, 6, this will connect to this element. So you can see that if 3, 6 is there, corresponding to that 6, 12 is also there. So if these two are there, then if 3, 12 is there, it will become transitive, and 3, 12 is there, so transitive it is. You can see that B option comes out to be true. Now this extremely simple question was asked in 2004. This question says that is the relationship which is defined over set A. A is given. So let us first check for reflexive. You can see that 1, 1, 2, 2, 3, 3, all of these should be present, but even 1, 1 is not there. So this is not reflexive. Second, if I want to check symmetric, you can see that 1, 3 is there, 3, 1 is there, this pair is fine. 4, 2 is there, 2, 4 is there. But for 2, 3, 3, 2 is not there. So it is not symmetric. So you can see that B option directly comes out to be true. Now let us look into this third problem type that is based on equivalence relation again, but the representation of relationship is different. It is written as X is related to Y. So what would this mean in terms of reflexive? So what should this mean? X should also be related to X for all values of X belonging to set A. If I want to write it in a symmetric manner or check the symmetricity, if X is related to Y, now this should imply that Y is also related to X. And in the third part, for checking transitive, if X is related to Y and Y is related to Z, this should apply that X is also related to Z. So we will have to check these three conditions to check for equivalence relation. If I look into this 2024 question, this is an interesting question, says that for 1, 2, 3, 4, 5, this is how a set A is given. We have been given a relation that 4x is smaller than equal to 5. Now what they are saying is if m be the number of elements in relation R and n be the minimum number of elements required from A cross A to make that needs to be added to R to make it symmetric, then what is the value of m plus n? So in order to do this question, let us make a small table where we will write all the x values along the x-axis and y values along the y-axis. Let us do this. If I write here 1, 2, 3, 4, 5 in this table, and correspondingly let us also draw columns and rows. So this is what I have. And correspondingly here let us also write 1, 2, 3, 4 and 5. And let us also draw rows here. So once I draw this, I have got a very simple table. Now you can see that here this is an element that is 1, 1, where x and y both are 1 and 1. Here there is an element that is 2, 2. Here we will have an element 3, 3, 4, 4 and simply 5, 5. See, once you have this, it is very simple to understand that if I put any of these values x and y is equal, it is obvious that since 1, 2, 3, 4, 5 are all positive values, your 5y will be greater than or equal to 4x. So all of these values will by default satisfy. So we can see that all of these values are will be required to be there in the relation, and these are all satisfying. If I take a value that is below this, so you can see that the value of x will remain same and the value of y will increase. So all of these values then that I am writing below, and that is nothing but 1, 2 will by default satisfy because 1, 1 is satisfying. So if I put 1, 2, you can see that this will become like this and this will also satisfy. You can see that all the values that are coming below this will also satisfy. So all the values here as well as here, all of this will also satisfy. There is no problem. Now let us check the value on the other side. So if I consider a value that looks like this, like 2, 1, and now let us check for these values whether this is satisfying it or not. So if I take 2, 1, what happens to this? So if I put 2, 1 in this relation that is given to me, let us see what happens. So 2, 1 will make this 8 and this 5. So this relationship will not satisfy. We can see that this will not satisfy. If I take a value just above 3, 3, that is 3, 2, will this satisfy? So this will make it 12 on the left hand side and 10. So this will also not satisfy. Similarly, let us check for 4, 3. That is just above this. This will be 16, is smaller than 50. This will also not satisfy. But if I look at a value that is just above 5, 5, that is 5, 4. And if I substitute, let us see what we are getting. So this will make this 20 and this will also become 20. So this is satisfying for the equal to sign. So this is fine. You can see that, but now if I consider value above this, that is 5, 3, this will not satisfy. So you can see that apart from 5, 4, all the values on the diagonal and below the diagonals are satisfying. And above the diagonal, only 5, 4 is satisfying, rest of them are not satisfying. You can see that how many values are there. The value of m if I want to find, now I can write all the diagonal value that are nothing but 5. And then non-diagonal values. So how to find this non-diagonal value? It is very simple. Total values are nothing but 25. If I subtract diagonal, I will get 20 non-diagonal value. Now half of them will be below the diagonal. So 10 are below the diagonal, 10 are above the diagonal. So all the diagonal values below the diagonal are satisfying, plus 1 above the diagonal is also satisfying. So if you add it up, this becomes nothing but 16. And if I want to find the value of n, it is above the diagonal minus 1. So 10 minus 1, this becomes 9. If you add m and n, it will become 25, hence option C satisfies. Now let us look into this 2022 question. Now in this question, instead of 1, we have been given 2 relations. This is first relation, this is second relation. So let us first check for relation 1, the equivalence relation. You can see that if I put A is related to A, so what will happen? This will become A square is greater than or equal to 0. For A belonging to real number, this is true. So you can see that it becomes reflexive. So the first part, reflexive part, is correct. Now what we are saying is, if A is related to B, that would mean AB is greater than or equal to 0. Then obviously BA will also be greater than or equal to 0. So B is also related to A. This part also comes out to be 2. This is symmetric as well. Now let us check for the third part, that is transitive. So if A1 is related to B, that would mean AB is greater than 0. B is related to C, that will mean BC is greater than or equal to 0. Now would this also mean AC is greater than or equal to 0? See, this might or might not be true, because if I take B is equal to 0, what will happen? And if I take the value of A as nothing but minus 2 and value of, so what will happen? A into B will be greater than or equal to 0. Similarly, now if I take the value of C as nothing but 2, now BC will also be greater than or equal to 0. But if you try and figure out the value of AB, it is not going to, AC, it is going to be smaller than or equal to 0. So you can see that this is not satisfying, so this is non-symmetric. So it is reflexive, it is symmetric but not transitive, hence not an equivalence relation. So this is non-equivalence. Now let us check for relation R2. So in the second part, A is related to B. This is what we are doing. So this would mean A is greater than equal to B. So if I do it for the first part, that is reflexive, A will be related to A. So A is greater than equal to A, that is fine because greater than or equal to, it is equal to. Second part is if A is related to B, that would mean A is greater than equal to B. So B is also related to A. So B should be greater than equal to C. This is not true. You can see that this is also not equivalent. So option D satisfies. Now if I look into this 2022 question, it is an interesting question. Question says that the relationship is given as 3x plus alpha y is a multiple of 7. They have given that alpha is a natural number. Also relation is defined on natural numbers. This is given to us. They are asking that for what value of alpha will this become an equivalence relationship. So if I just take the first condition of reflexive, I should get my answer. So what we are saying is if I put x comma x, it should satisfy. In place of y, let us also put. So this should be a multiple of 7. So now you can see that this is 3 plus alpha into x should be a multiple of 7. Now this should be true for any natural number x. So in the worst case scenario, this might not be a multiple of 7. Like if I put x equal to 1, it is not a multiple of 7. So for this to satisfy, it is essential that 3 plus alpha should be a multiple of 7. If I do this, now you can see that alpha will become 7 n dash minus 3. So you can see that if I divide alpha by 7, the remainder is minus 3. Now minus 3 remainder is not possible because it needs to be number between 0 and 6. So what we can do is we can add 7. So this will become 7 n dash minus 1. So what we have done is we have subtracted 7 and added 7 at the same time. You can see that the remainder will become 4. And generally, if we are writing minus 3 as remainder, so we'll have to add 7 to make it positive. So it will become plus 4 remainder. You can see that option D comes out to be true. Now let us look into this next 2021 question. Question says that x and y are two such elements that satisfy this relation over natural numbers. Now this is also important what is given to us. Now if I write this relation, let us see what is given to us. So this would mean x cube minus xy square I can group together. And then the remaining thing minus 3 x square y plus 3y cube I can group together. Now from here I can take x common. So this becomes x square minus y square. From here I can take 3y common. So this again becomes x square minus y square. So you can see that this can be ultimately written as x minus 3y into x square minus y square equal to 0, which can in turn be factorized as x minus 3y, x minus y and x plus y equal to 0. What does this essentially means is this relation would get satisfied for elements for which x is equal to y from here, for x is equal to minus y from here, and for x is equal to 3y from here. Now we know that since it is defined over natural numbers, this makes no sense. So if I want to write the relation, you can see that from x equal to y, we will have things like 1 comma 1, 2 comma 2, etc. satisfying this. You can see that it will become reflexive because of this. But let us say that if I have y is equal to 1, corresponding to that, the value of x will become 3. So you can see that there is 3 comma 1 here. But 1 comma 3 will not belong to this relation. And that is the reason it is not going to be symmetric. So it is reflective but not symmetric. Let us check the option. So you can see that option B satisfies. Now this type 4 questions based on equivalence relationship are based on relation of ordered pair over ordered pair. Now this is different. Earlier we were trying to connect one element with another element. Now we are trying to connect two ordered pairs. That would mean if I want to show something as reflexive, I will have to prove this. A comma B is related to A comma B. So we are showing the two same ordered pairs should be linked to each other. Second, if I want to show symmetric, again the idea would change from if A comma B is related to C comma D, then C comma D should also be related to A comma B. This is what should be shown. And then for the third part, that is transitive. Now we will have to again go from ordered pair. A comma B is related to C comma D, and C comma D is related to E comma F. Then we'll have to show that this implies A comma B is related to E comma F. Now if I look into this 2024 question, it exactly talks about similar kind of ordered pair related to ordered pair kind of a scenario. You can see that it is defined over Z cross Z. Earlier it was only defined over Z. So this is the reason what is this kind of relationships are getting formed. Now question clearly says that if A comma B is related to C comma D, the relation is AD minus BC should be a multiple of 5. This getting multiplied to this getting multiplied to this. So if I want to check the first part, that is a reflexive part, what I will check is A comma B getting related to itself. So if I replace C by A and D by B, this will become AB. This will become, and we are replacing C by A, so this will become BA. You can see that this will become 0, hence a multiple of 5. So it becomes reflexive, there is no issue. For the symmetric part, now what you will have to check is nothing but if A comma B is related to C comma D. So this would mean AB, AD minus CB, BC is a multiple of 5. So what should happen is CD should also be related to AB. So now what will happen, this will get multiplied to this will get multiplied to this, and you will essentially get CB minus AD. So you can see that if this is the multiple of N, this will also become a multiple of N. So that is totally justified, this will also symmetric. Now in the third part, we will check this same relationship for transitive. So for transitive, A comma B should be related to C comma D, this we are assuming, and C comma D should be related to E comma F, this also we are assuming. From first one, AD minus BC is equal to 5 and 1. From the next one, we have CF minus DE is equal to 5 and 2. And from here, we'll have to go and prove that AB is related to EF. And that will essentially mean we have to prove AF minus BE will be a multiple of 5 as well. Now we can see that there is no way to connect these two ideas, hence it will not be transitive. So it is reflexive, it is symmetric but not transitive, hence option B comes out to be the correct answer. Now you can see that this same question was again asked in 2024, similar type, but they are again now connecting two relations. So let us first talk about R1. R1 says that A is related to be such that A square plus B square is equal to 1. So we have been given this relation. You can see that if I put A comma A, this would mean twice of A square will be equal to 1. Now we can see that this is defined for all real numbers, so this is not true. So even this is not reflexive. If I move towards relation 2, and this is the one that we were discussing earlier. So let us rewrite the statement that is given to us. I can write this as A minus B is equal to C minus D. So in the first part, if I want to check for reflexive, I need to check whether A comma B will be related to A comma B. That would essentially means A minus B will be equal to A minus B, and this is largely true, there is no issue with this. In the second part, I will go and check for symmetric. So that would mean A comma B should be related to C comma D. Then C comma D should also be related to A comma B. So you can see that if A minus B is equal to C minus D, then of course C minus D will also be equal to A minus B. So it is also becoming symmetric, there is no issue. And in the third part, for checking transitive, we will have to check whether A comma B is related to, if this is related to C comma D, and C comma D is related to E comma F. So this would mean A minus B is equal to C minus D. And the second statement would mean C minus D is equal to E minus F. So automatically from here we can write A minus B will be equal to E minus F. Hence A comma B is related to E comma F. you can see that it becomes transitive. So it is all three reflexive, symmetric, transitive, hence only R2 is an equivalence relation. If I look into this 2024 question says that this ordered pair is related to this ordered pair in the format that there is an OR relation between them. So x1 should be smaller than equal to x2 or y1 should be smaller than equal to y2. So you can see that from the prima facie that it is going to be reflexive, because if I put x1 comma y1 and then check it is related to again x1 comma y1, what is going to happen is this will become x1 is smaller than equal to x1 or y1 is smaller than equal to y1. Both of these statement is true because it is smaller than equal to sign. So reflexive part is fine. Next, let us go to the symmetric part. So now we can say that if x1 comma y1 is related to x2 comma y2, the opposite should also be true. So x1 is smaller than equal to x2 or y1 is smaller than equal to y2. And what it is saying that the opposite relationship, that is x2 is smaller than equal to x1 or y2 is smaller than equal to y1 should also be true. Now this cannot be true, so it is not symmetric. Now for checking the third transitive part, let us take this example. So if I am relating 4 comma 8 to 5 comma 6, this will get satisfied because you can see that 5 is greater than 4. It is not getting satisfying for the second part, because what we need to check is either 5 is greater than or equal to 4 or so there is an all condition. So if the second condition is not getting satisfied, it is totally fine, it does not matter. And you can see that for the second one it is still satisfied because second condition is true but first is not true. But now you can see that despite this being true, 4 comma 8 is not related to 3 comma 7 because it is not true for either x1 or y1, and for those both the condition is not true, so this is not present. Hence you will see that this option will become correct. Statement 2 is incorrect, 1 is true, so you will see that D option will come out to be correct. Now let us go into type 4 problem where we have to check equivalence relationship between sets or using set theory. Now this was a question in 2024. You can see that the question says that there is a set S and M be a set of all subsets of S such that if I take two subsets, then the intersection should not be null set. This is what the condition is. Now if I want to check reflexive, then the condition is A intersection A should not be a null set. But see, this condition will get violated if I make a subset out of this which has nothing into it. It is totally possible to make a subset like this, and then if I take a subset, it will become subset, so this condition will get violated, so it is not reflexive. If I move towards the second part and go for symmetry, now we are saying that if A intersection B is not equal to null set, so it is obvious that B intersection A will also not be null set, and this is fine, there is no issue with this. In the third part, if I go to the transitive part, what we are saying is if A intersection B is not equal to null set and B intersection C is not equal to null set, then what happened to A intersection C? Now let us take an example. If I take A as nothing but 1 and 2, B as nothing but 2 and 3, and C as nothing but 3 and 4, so you can see that despite A and B and C not having the intersection as non-null set, but A and C, if you check out, A intersection C is going to have null set, so this is not getting satisfied, so it is non-transitive. If you check the option, A option comes out to be true. Now this very interesting question was asked in 2023. This question says that if PS is a power set over this set S that is given to us, and R1 and R2 are a set again defined on PS. Now all of this will not be required in solving this question. You just need to look into relation 1. What they are saying, if I draw the Venn diagram, this is A, this is B. So what they are saying is A intersection not B, that would mean this portion is equal to this portion. Union if I take is equal to null set, that would mean there is no element here. So if I want to put any element, it will come here. That will essentially mean every element that A will have, B will also have. So essentially A is equal to B. Now if A is equal to B, then if I want to check reflexive, so if I put A in place of A, it will still be true. If I want to check symmetric, if A is equal to B, obviously it will also mean B is equal to A. This will also become true. And for transitive, if A is equal to B and B is equal to C, obviously C will also be equal to A. This will also become true. So you can see that all of them are satisfying. This becomes an equivalence relation. In the second part, if I look into relation 2, now what they are saying here is again very interesting. Now what they are saying is A union not B is equal to B union not A. See, if you put A is equal to B here directly in the relation, you will see that it will directly satisfy. So it is becoming reflexive, there is no issue. If I reverse A and B, the relationship will not change. So symmetric, automatically it is happening. Only we need to check for transitive. Now if you closely observe, what they are saying is A union not B. So A will definitely come and not B will also come. So you can see that this portion is equivalent to, if I draw another Venn diagram, so you can see that this portion is equal to this portion. See, this can only happen when again A will become equal to B. So this is the same case as the first case. So this will also become equivalence. Hence, C option comes out to be true. Now, type questions are based on equivalence relationship in which matrices get involved. If I look into this 2021 question, it is an interesting question because they have given A is related to B if there exists a non-singular matrix B such that PA P inverse is equal to B. See, let us go to the relationship first. So PA P inverse is equal to B. So if I do post multiplication of P, this will become PA is equal to BP. This is the relation that they are talking about. This should be true for some value of P, that is non-singular matrix. So that would mean identity matrices or matrices are totally fine. Now if I want to check reflexive, that would mean PA should be equal to AP, and this should be true for some value of P, and that is true because if I put P is equal to Y, this will get satisfied. There is no issue. Third is we will need to check symmetric nature. So what we are saying is if PA is equal to BP, then PB should be equal to AP. Now this again is true if I put P is equal to Y. So one value of P is there where this is happening, so this will also become true, there is no issue. And similarly in the fourth part, transitive will also happen using similar logic. So this becomes an equivalence relation. Now let us look into type 6 problem type, that is equivalence class. Now what is the equivalence class? In order to understand this, let us take an example. X minus Y is equal to an even integer. Here X and Y both belongs to Z. If we have this, you can see that out of this set of integers Z, if I consider both X and Y as odd, then this relation will get satisfied. If I consider both of them as even, then it will get satisfied. But if I take one even, one odd, it will not get satisfied. So what this relation has ultimately done is, this equivalence relation has divided the original set into two classes. In these classes, if I take any two elements from the first class, it will satisfy. If I take two elements from the second class, it will still satisfy. But if I take one from the first, another from the second, it will not satisfy. Wherein if I take union of both of these, it will become the original parent set, that is nothing but set. So if this happens for an equivalence relation, we would say that equivalence class exists. Now there was a question based on the idea, vaguely based on this idea, but it came in 2021. Question says that P and Q are at the same distance from origin. Then the equivalence class of 1 comma minus 1 is the set. See, the distance of 1 comma minus 1 from the origin would be nothing but root of 1 square plus minus 1 square, that will become nothing but root 2. This is what we have. So if I take a point x comma y that is of the same class, it should also satisfy this relationship. So the distance from the origin, that is x square plus y square, should also be equal to root 2. And hence, if I simplify this, x square plus y square should be equal to 2. That becomes option 4. Now this type 7 problem type is based on counting or P&C and relations. Now this question came in 2024 that says that number of symmetric relations between the set 1, 2, 3, 4 which are non-reflexive. So see, if I want to make it reflexive, in that scenario what I will want is all of these elements 1, 1, 2, 2, 3, 3, 4, 4. All of these 4 needs to be there. So you can see that either one of them will be present or absent, can happen into 2 into 2 into 2 into 2 cases. There are total 16 cases. Out of this 16, in only one all of them will be present. So out of this, in 15 cases, it will become non-reflexive. So first part we have taken care, first condition. Now in second condition, they are saying that it needs to be symmetric. Now we can see that for symmetric, if I take 1, 2, then 2, 1 also be there, should also be there. So we need to figure out how many such pairs are there. So you can see that if I take 1, 2, correspondingly 2, 1 would be there. So if I want to make such x, y elements, how many such elements? So first place can be filled using 4 ways, second using 3 ways. So total such 12 elements would be there, and half of them would be pairs. So if I take 1, 2, then 2, 1 is there. So you can see that there are 6 pairs in this manner. So if we want to make it symmetric, we will have to either take a pair or exclude a pair. So out of this 6, the pairs can be either present or expand in 2 raised to the power 6 ways. So total ways of this happening would be nothing but 15 for it to become non-reflexive and 2 raised to the power 6 for it to become symmetric. Hence the answer of this question becomes nothing but 960. Now this interesting 2024 question is a very famous question. It says that there is a set A given, there is a set R given. We want to make an equivalence relationship S in such a manner that R is a subset of S. This is what we want to do. So what they are saying is minimum number of element in S is n, then we want to find the value of that n. So let us write things down. So if you want to make it reflexive, what are the elements we need to have is 1, 1, 2, 2, 3, 3 and 4, 4. Now in the next part, if I want to make it symmetric, let us see what else will require. So 1, 2 is there because R is a subset of S. 2, 3 is there. 1, 4 is there. So corresponding to 1, 2, you will require 2, 1. Corresponding to this will require 3, 2 and then 4, 1. Now we will also want to make it symmetric in the third place, transitive in the third place. So for making it transitive, you can see that if you have 1, 2 and then 2, 3, so 1, 3 also needs to be there. And since you have added 1, 3, to make it symmetric, you will also require 3, 1. So this also will get added up in the list. Now if moving forward, you can see that what we have is nothing but 2, 1 and 1, 4. So in order to make this transitive, you will require 2, 4. And in order to make that symmetric, you will require 4, 2. You can see that 2 elements more got added more. Now since we have this, you can see that corresponding to this 3, 4 also we require, because again we will need to make it transitive. So 3, 4 we will add, and correspondingly also need to add 4, 3 to make it symmetric. So now you can see that the total number of element, how many have we got? So we have got 4 here, 4 here 8, 4 here 12 and then 4 here, nothing but 16. So total number of elements or the value of n comes out to be 16.
If you like this video, you will also like PracBee's unique one-on-one last mile journey program. In this program, we sit with the student, understand their preparation till this point of time. And based on that, in step 2, we write a customized planner just for you to help you optimize your marks in JEE Mains exam based on whatever preparation you have done. In the step 3, we sit with you one-on-one by a set of faculties aligned by PracBee and help you implement the customized plan that we wrote for you. Students have come to us with limited no or good preparation and all have been able to score their marks to a large extent. Ashish, using this program, was able to improve his fortunes by lot, starting from 95 percentile in JEE Mains attempt 2 to getting selected for mechanical in IIT Madras. Ditya, over a period of time, was able to crack into JEE Advanced using this program. If you think that this seems interesting to you, click on the link below in the description, fill the required details and somebody from my team will get in touch with you.